Section 6.5, Rational Functions and Rational Inequalities. This section, we are going to look at the characteristics of rational functions, vertical asymptotes, horizontal and oblique asymptote, graphing rational functions, and solving rational inequality. Let's look at the characteristics of the rational function. The first one, by definition, a rational function is a function that can be written in the form of f of x equals px over qx, where qx and px are polynomial functions, and the qx cannot be zero. Given the rational function px over qx, the domain of this rational function consists of all real numbers except those for which the qx equals 0. The next one is about the vertical asymptote. The vertical line x equals c is a vertical asymptote of a function f if f increases in magnitude without bound as x approaches c. As you see the first graph, c equals 2, the graph increases without bound as x approaches c, both from the left and from the right. The second graph, c is 2, the value of the function increases without bound but in a negative way, both sides of x equals 2 as x approaches 2. The third graph, as x equals 2, it could be in the behavior that the function on the left approaching negative infinity or decrease without bound, where the right-hand side of the line x equals 2, the graph increases without bound. The next one is the horizontal asymptote. It is the horizontal line in the form of y equals c if the function f of x approaches the value c, or we can write the notation like y value approaching c as x approaches negative infinity or as x approaches positive infinity. That means we look at the two ends. The first end, when x approaches negative infinity, what is the behavior of the graph as y approaching 2? And on the other end, as x approaches positive infinity, what happens to the behavior of the function value? Left end, right end, left end, right end. Next one, the oblique or slant asymptote. An oblique or slant asymptote is a dashed line on the graph describing the end behavior of the function approaching a diagonal line where the slope is neither 0, which is a non-horizontal line, nor undefined, which is a non-vertical line. So basically, the slant asymptote is an asymptote with a slope, or they will be represented by the function like y equals mx plus b. Next part, asymptotic notation. The notation x approaches c negative is used when describing the behavior of the graph as x approaches the value c from the left or the negative side. The notation x approaches c positive is used when describing the behavior of the graph as x approaches the value of the c from the right, which is from the positive side. The notation x approaches c without the superscript plus or minus sign is used when describing the behavior that is the same on both sides of the value c. The vertical asymptotes. Vertical asymptote theorem, equations for vertical asymptotes. The rational function f of x equals px over qx has been written in reduced form, where p and q have no common factors. The vertical line x equals c is a vertical asymptote of f if and only if c is a zero of a polynomial q. In other words, f has vertical asymptotes as x-intercepts of q. These examples, we are going to find the domain and the equations for the vertical asymptotes of the following function. From the original function here, to find the domain for the rational function, we're going to have to look for the number that make the denominator to be 0. So 3 minus x equals 0. Therefore, x equals 3. It will tell you that the domain of this function is the set of x such that x cannot be 3. And where the vertical asymptote, we look at the reduced form. Reduced form of this fraction means if we can factor or reduce, we do it until we cannot do anymore. And this is already in the most reduced form. So from the most reduced form here, we can see that the denominator, which is 3 minus x, at the 0, x equals 3, will tell us x equals 3 is a vertical asymptote for this function. For this problem, we are going to find the domain and the vertical asymptote. First part, when we are going to find the domain, we're going to look at the original function. So from the denominator, 2x squared minus 18, we're going to look at the 0 for this, factor completely. We have 2 times x minus 3, x plus 3 equals 0. Therefore, x equals 3, x equals negative 3, gonna make it 0. We can wrap it up by the domain of this function is the set of x such that x cannot be 3, cannot be negative 3. So we have to omit these two numbers from the set of our real numbers. Domain part is done. Next, we're gonna find the vertical asymptote. For the vertical asymptotes, we have to use the reduced form of the function. To find the reduced form, we're gonna have to factor completely. So I'm gonna recopy the function, which is x squared minus x minus 6 divided by 2x squared minus 18. The denominator already factored when we look for the domain to have like 2 times x minus 3, x plus 3. The numerator factor completely to be x minus 3x plus 2. We can see the common factor that we can reduce, which is x minus 3, x minus 3. Therefore, the reduced form of this function is x plus 2 over 2 times x plus 3. That's the reduced form. And from the reduced form, the denominator gonna tell you what is your vertical asymptote. That means whatever the number that make x plus 3 to be 0 or x equals negative 3, that means the vertical asymptote is x equals negative 3. In this example, we have f of x equals 2x squared minus 3x minus 20 divided by x plus 2. First, when we look for the domain, consider the denominator. Which is x plus 2. When x plus 2 equals 0, x is negative 2. This will tell us the domain is the set of x such that x cannot be negative 2. Next, we're going to find the vertical asymptote. For the vertical asymptote, we're going to consider the simplified form of the function or the reduced form. what we have as the f of x, or 2x squared minus 3x minus 20 divided by x plus 2. Let's see, we can factor more for the numerator. So we're going to factor the 2x squared minus 3x minus 20 using the AC technique. A is 2, C is 20, negative 20, sorry, it is negative 40. And then we're going to find a pair of the numbers that these two multiply to be negative 40. That means one negative side, one plus side. But the sum is negative 3. We find negative 8 here and positive 5. That help us to break it down into 2x to the second minus 8x plus 5x minus 20. The middle term here, which is from negative 3x, now is broken into negative 8x plus 5x. And then use the grouping technique to have 2x squared minus 8x plus 5x minus 20. Common factor 2x for the first group. We have x minus 4 in the parentheses. Common factor 5 for the second group. Inside parentheses is x minus 4. Then we factor completely to have the factor 2x plus 5 and x minus 4. Now we bring it into the main part of the problem. So the function has the factor form of the numerator as 2x plus 5 times x minus 4, all divided by x plus 2. We do not have any common factor, so this is the most reduced form. Therefore, we look at the 0 for the denominator. So x plus 2 equals 0, or x is negative 2. Therefore, we have x equals negative 2 as a vertical asymptote for this problem. To wrap up the domain, x not equal to negative 2, the vertical asymptote x equals negative 2.